Good evening, everybody. This is the end of everything. As you can see from the subtitle, it's talking about the fate of the Earth, the fate of the Sun, the fate of the galaxy, and ultimately, if time allows, the fate of the universe. It'll take us a while to get to that point, but if it takes 3 or 4 hours, so be it. Perhaps a better subtitle would be something like that. I couldn't get the soundtrack to go along with that because, of course, he never actually says that. It's only infinity and beyond. But eternity is just as difficult to get your head round. So what we're going to do in this talk is, apart from a little bit of a prologue, which might overlap with your previous talk last month, I'll be talking about the future of the Earth and the Sun and the solar system, looking further ahead into the future, looking at the future of stars and galaxies, and then into the far, 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 far future, looking at the ultimate fate of the universe. And then I'll finish with a little epilogue. I'm not necessarily going to be covering this topic by topic. I'm going to try and keep it in chronological order. So I might be jumping around a bit between what the Earth's doing, what the Sun is doing, what the galaxy is doing, but I'll try and keep it in a timeline order. So just a very quick recap. The story so far. The universe exists, you may have noticed, okay? So in a different talk, which probably overlaps with your last month's talk, I talked about the beginning of everything and how everything that we see in the observable universe, at the moment the observable universe is everything inside a sphere, something like 100 billion light years across, centered on us. That's what we define as the observable universe. In the past, everything used to be a lot closer, and everything inside the observable universe used to be inside a volume approximately the size of a golf ball. In 3 minutes, the universe made all the protons and all the neutrons necessary to make all of the hydrogen and all of the helium that we see in the universe. It only takes 3 minutes to make a universe. And once we've got all the hydrogen, the rest is easy. We can figure out, given hydrogen and given, if we wait long enough, we can understand galaxies and stars and planets and trees and mountains and snowflakes and rainbows and cats and okay, maybe not cats. We'll never understand cats, but we'll understand everything once we've got the hydrogen made. Now we're going to say, right, let's assume we are where we are. 13.8 billion years ago, the universe came into existence. In 3 minutes, all the hydrogen was made. And since then, the universe has been using stars to make helium and carbon and nitrogen and oxygen and us and other things. Now, to try and keep track of the timeline, because it's going to get very confusing because we're going to jump forward in lots and lots of time steps, I thought I would try and keep track of where we are with this timeline across the top here. Each small box in the timeline represents 10 times further into the future. So we're talking about a logarithmic scale, essentially. So in other words, the top left is effectively now, if you want to think of it as that. I am not going to be talking about where we're going to be in 10 years' time. That depends on Boris and a few other politicians and climate change, etc. I'm going to start at about 1,000 years, 10 to the power 3, 1,000 years into the future. And then we're going to go through year by year, or rather factor of 10 by factor of 10, 10 to the 4, 10 to the 5. We'll be looking at 1 million years into the future, and then we'll keep going, and we'll be looking at 1 billion years into the future, and we'll keep going, and we'll be looking at 1 trillion years into the future. That's not where it ends, but that will do for now, just to give us an idea. And these red boxes will basically go along that timeline to remind you where we are at in terms of years into the future. And before I forget, let me acknowledge the fact that these two individuals, Adams and Laughlin, published a paper some years ago in which they tried to calculate the astrophysical timeline of what is likely to happen in the future. There were some things we don't know, but there were some guesstimates, some rough estimates of what is going to happen when, and I used that particular paper to try and get the chronology right. So I've got lots of things happening, jumping around Earth, Sun, galaxy, universe, and I've attempted to keep them in chronological order, thanks in part to this paper. So thank you guys for calculating these things. Right, we're going to start 1,000 years into the future. We're going to assume that mankind has not trashed itself completely, that we haven't destroyed ourselves, and that we've got climate change under some sort of control. In 1,000 years' time, a separate talk, I talk about why we need leap seconds, because the Earth's rotation is slowing down. We can tell the Earth's rotation is slowing down because we've had atomic clocks for a little while and we can see the slowing down. In 1,000 years, instead of the necessity of adding leap seconds to our clocks to keep the rotation of the Earth synchronized with our clocks, instead of adding leap seconds every few years, in 1,000 years, the Earth's spin will have slowed down to the point where we need to add leap seconds every few weeks. And we will see the effect of that as the Earth continues to slow down into the future. Now, it's possible that some stars are going to explode in the next 1,000 or 10,000 or 100,000 years, let's say 10 to the 4 years. But of course, we can't predict this exactly. We might say Antares is likely to go supernova sometime, but we cannot with any certainty say when that is going to be. But there are some things in our future that we know are going to happen. For instance, we know the spin of the Earth is precessing. In other words, the direction of the Earth's spin, let's assume it's still spinning roughly once in 24 hours, but the direction that the Earth's spin is pointing is changing because of the gravitational pull of the Sun and other planets. And you can see here that it's cyclic in the sense that the direction that the Earth's axis points traces out a circle in the sky, and it takes about 26,000 years for that circle to be complete. So in other words, if we look on the sky as to where the Earth's axis is pointing, at the moment the Earth's axis is pointing roughly in the direction of Polaris. That's why we call it the North Star. But it's not always going to be that way. In 26,000 years it will have moved, and eventually it will come back to Polaris. But if we think of about half that time scale, in approximately 10 or so thousand years, the axis of the Earth is going to be pointing in the other direction on the sky. In other words, it's going to be quite close to the bright star Vega. A lot of people seem to think that the pole star, for some reason, is one of the brightest stars in the sky. We know that Polaris isn't that bright, but if you wait 10 or 12,000 years, the pole star will be one of the brightest stars in the sky. Why should that make any difference at all, whether or not the axis of the Earth is pointing at Polaris or whether the axis of the Earth is pointing at Vega? Well, if we think about where the Sun is in its elliptical journey around the Sun, at the moment, the Earth is closest to the Sun, perihelion, in northern winter. In other words, the axis of the Earth is pointing away from the Sun when we're closest to the Sun. This tends to moderate the seasons somewhat. But if the axis of the Earth is pointing in the other direction, that means we'll be closest to the Sun, assuming the Earth's orbit doesn't change drastically. We'll be closer to the Sun during northern summer. So in other words, we'll get a little extra heat from the Sun because we're closer, at the same time that we're getting a lot of heat from the Sun because we're tilted towards the Sun. So in other words, the seasons are going to be a little more extreme in 10,000 years' time, simply because of the precession of the Earth, the change of the Earth's axis. And any climate changes, which are nothing to do with us, but are a function of the way the Earth's spin changes or the way the Earth's orbit changes, these are called Milankovitch cycles. And if you wish to learn more about that, you can go and look it up and find a Wikipedia article about Milankovitch cycles. So the Earth's precession will give us different seasons regardless of what we try and do about climate change. The climate will definitely change because of these cycles. On a scale of about 10 to the 5 years, so we're now talking about 100,000 years into the future, we know that the Voyager probes were launched in the 1970s, and they've gone flying past Jupiter, Saturn, Uranus, Neptune, etc. for Voyager 2, rather less for Voyager 1. They have now officially left the solar system, and they are heading off into deep space. Voyager 1 in the top left here will head off, and on a timescale of about 40,000 years or so, it'll pass the star called Gliese 445. Voyager 2 down at the bottom here is heading off in a different direction, and on a similar timescale, it's going to pass the star Ross 248. Pioneer 10 and Pioneer 11 were launched a few years earlier than Voyager, but they were traveling more slowly, so they're not going to actually reach the nearest stars before the Voyager probes do. Pioneer 10 is actually heading off in the direction of Aldebaran. Pioneer 11 is heading off in the direction of the center of the galaxy. So we'll come back to Voyager. Let's just remember that the timescale on which they're expected to pass stars is of order tens of thousands of years, and then they'll pass another star in a few tens of thousands of years. Then they'll probably pass another star in tens of thousands of years. Let's return to the Earth. What is it doing? Well, historical records tell us that there are repeating cycles of glacial and interglacial periods. We just call them ice ages usually. And they tend to occur on timescales of order 100,000 years or so. So we can see that from the historical record. We know that Earth entered a warmish phase fairly recently, and therefore it's likely that we'll get an ice age again in about 100,000 years. In other words, ice will come down from the pole and will start covering parts of Europe, for instance. That's another manifestation of Milankovitch cycles. It's again due to the changes in the Earth's orbit and changes in the Earth's spin. If you go back a long, long, long way, we have evidence that the Earth might have been a snowball. In other words, the ice might have covered the entire planet. This is still a hypothesis rather than proven, but that's a sort of a perfect storm, if you like, of lots of things coming together and cooling the Earth. But the ice ages, we know, are on a timescale of about 100,000 years. So we can expect the Earth's climate to change again on that timescale, regardless of man-made efforts to keep it under control. On this timescale, the Earth is still slowing down. The Earth is slowing down because the moon is pulling on it. The moon is raising tides on the Earth, slowing the Earth down, and effectively the moon is robbing some of the angular momentum from the Earth. On this timescale, 100,000 years, leap seconds don't need to be added every few years or every few weeks. We would need to add a second to our clocks every day to keep our clocks synchronized with the rotation of the Earth. In other words, the rotation of the Earth will be about 24 hours and 1 second. So in other words, our clocks will need adjusting either all the time, or perhaps we'll throw away the idea of 24-hour clocks. Maybe we'll have gone decimal by then, and we'll have 10 hours in a day or 100 hours in a day. Who knows what we decide to do. But the Earth will continue to slow down. We don't know which stars are going to go supernova. We know of some definite candidates, like Eta Carinae in the southern hemisphere. When the Hubble Space Telescope looks at it at the moment, it sees these huge plumes of gas that have been ejected from the surface of this particular star. It appears this star is so unstable it can't hang on to its outer envelope. And for many thousands of years, it's been expelling lots of this material into interstellar space. We think that's a sign of it coming towards the end of its life, but we can't tell exactly when it's going to go supernova, but it's definitely a candidate, and it's thought that it might go on a time scale of something like 100,000 years. The same is true of Betelgeuse. You might have heard the scare that we thought maybe Betelgeuse was on the verge of perhaps getting towards the end of its life a little while ago. Turns out it was probably just dust around the surface of the star, blocking some of the light. This is a picture taken, as you can see here, from Prague. Somebody took this beautiful picture of the night sky with an observatory in the foreground, and then definitely went into Photoshop to add what would that same scene look like if Betelgeuse went into its supernova phase. So it's a genuine picture that's been photoshopped to give us an impression of what it might look like when Betelgeuse goes supernova. So perhaps you can see the three stars of the belt and the familiar outline of Orion, but it's a little more tricky to pick out Orion when the top left shoulder is blazing away so brightly. Betelgeuse is quite a few hundred light years away, but it will probably still be visible during the day when it does decide to go supernova. There are some stars that are more dangerous than others. We'll talk a little bit later about stars that might go supernova close to us. There are certain types of star, don't worry about the name, that's just the type of star, Wolf-Rayet stars. This particular one is 7,000 light years away. That sounds like an enormous distance, 10 times further away than Betelgeuse. Surely this can't be a problem. But if this star dies, the radiation burst could be more of a problem for us than even the much closer Betelgeuse. And that's because rapid rotation of this star system produces these jets. And if we happen to be in line with one of these jets, there could be a huge amount of radiation that comes out. And if those jets happen to be pointing in our direction, or one of those jets is pointing in our direction, that could be a problem. It's been calculated that if we're unlucky enough to be on a direct line of sight of this jet, it could actually, even from that distance, it could, for instance, produce enough radiation to strip the atmosphere or boil the oceans. So it could remove our biosphere. Luckily, people do not think that the jets are pointing precisely in our direction. So if they're a few degrees off, we might miss the worst of this if this decides to go supernova on a timescale similar to Eta Carinae, on a timescale of order 100,000 years or so. As stars go around the Milky Way, occasionally they get a little bit close to each other. On the whole, stars avoid each other. But given that we are going around the Milky Way along with all the other stars in our neighborhood, every once in a while we just might happen to get a little bit close to one star. And there's a star called Gliese 710, which is going to come close to us and then disappear again, get further away. That's not what the star is actually doing. It's the fact that both of us are going around the center of the Milky Way, and it's a consequence of looking at the motion of two stars going around a third body. So Gliese 710, on this sort of time scale, we're now talking about 1 million years into the future, by tracking where all the stars are and how fast they're moving, we can predict fairly accurately that Gliese 710 is going to come close to us. And close means within the Oort cloud. So the Oort cloud is a huge cloud of trillions of icy objects, and when this star gets into the Oort cloud, it's going to be like a fox in a hen house. It is going to completely disrupt the Oort cloud, and loads of asteroids and comets are going to be falling into the inner solar system when this gets to this sort of position here, somewhere inside the Oort cloud. It'll probably start disrupting it even when it's some distance away. So we are bound, if we're still in Earth and still living and still watching the skies, that we're bound to be a huge number of asteroids and comets heading our way. It's been estimated that there might be a naked-eye comet every month for 1 million years as this star comes into the Oort cloud and then disappears again. For a brief period, our solar system will actually have two stars in it. It'll have two suns, the familiar Sol plus Gliese 710. So get your cameras ready, because there's going to be a photo opportunity like you've never seen before whilst the solar system has two suns. Not quite like that, perhaps, but you get the idea. On a similar time scale, millions of years into the future, you might think this is a picture to say we might get bombarded every 1 million years or so. No, that's not what this picture is saying. Apart from the fact we can look at this and say, wow, something hit there. Wasn't it lucky? It just missed the visitor center. This is not supposedly saying that this is happening every 1 million years. What it's saying is, on a scale of 1 million years, we would expect weathering systems on the Earth to get rid of it. So we can see that quite clearly because it's only tens of thousands of years old. But on a scale of millions of years, that will be eroded by wind and rain and freezing and warming, and to the point where we might not even be able to see it as a crater anymore. And you might think that that's something peculiar to Earth. Surely on the moon there isn't any weathering, so things will last forever. Well, not quite, no. If we think, for instance, of Apollo footprints, the moon is actually, although there's no weathering systems because there's no atmosphere, there is a constant bombardment of micrometeorites. And what that means is that anything we see now won't last forever. Micrometeorites will pummel the surface. That's why the surface is effectively a rather fine talcum powder type dust. It's because all the rocks on the surface of the moon have been pummeled for the last billion years by micrometeorites. It's been estimated that the footprints might only last 1 million years, but even the lunar lander and the rover and all the other stuff that's been left on the surface of the moon will not last forever. Eventually, meteorites will effectively erase it to just base metal. I said that Pioneer is leaving the solar system just like Voyager's, and they might encounter other stars every 10,000 years or so. On a timescale of 10 million years, so remember this is 1,000 times longer, it might take 10,000 years to reach the next star, and another 10,000 years for the next star, and another 10,000 years for the next star. On a timescale of 10 million years, Pioneer might have passed, I don't know, 1,000 different stars, and a number of them might have Earth-like planets, and some of them, who knows, might have civilizations. In order to say hi, the Pioneer spacecraft have a plaque on the side which basically says this is who we are, this is how big we are compared to the spacecraft, and the picture on the left says this is where we came from in terms of a galactic coordinate system, if you like. But after 10 million years, that plaque will start to erode. Again, you think, well, it's in space. Why should it possibly erode? Well, space is not empty. It's full of the interstellar medium. Lots of atoms, maybe a few particles of dust as well, And if you've been traveling for millions of years, plowing your way through the interstellar medium, you will erode any piece of metal. In other words, it will get pitted with lots of micrometeorite impacts effectively. So after, let's say, about 10 million years, it'll be impossible to read that plaque. But meantime, it will have done its job of passing 1,000 different stars with possibly 1,000 planetary systems, possibly many hundreds of Earth-like planets, and it might have got the message to those Earth-like planets that this is who we are and this is where Pioneer came from. After 10 million years, they might find the spacecraft, but no one will be able to read the plaque because it will be effectively unreadable. We're now jumping ahead to many millions of years. We're now at 10 to the 8, 100 million years, and we can ask about Saturn's rings, and it helps to look backwards before we look forwards. How did Saturn's rings form in the first place? Simulations have indicated that maybe a moon like Mimas actually made Saturn's rings. And if you look at that moon, you might think to yourself,
that's no moon, it's a space station.
Because it certainly looks more like the Death Star than a moon. But it's thought that maybe if a moon like Mimas, this is the early Saturn with no rings, maybe if a moon was pummeled, perhaps by a collision with another moon, or more likely a collision with a comet coming streaming in from the Oort cloud, it's been calculated that the debris from that moon that's completely smashed eventually forms a ring system. Notice it doesn't take very long. Only takes a matter of days for a pummeled moon, the debris from a pummeled moon, to actually spread itself around the planet. Now, it takes a little while for the ring system to settle down. Over millions of years, the particles in the ring system start to migrate inwards towards the planet. And this is what we know and love now. This is a picture from the Hubble Space Telescope. But it is ephemeral. That's what it looks like now because the particles are slowly moving inwards. And we think on a timescale of order 10 to the 8, roughly speaking 100 million years, the ring system will continue to move inwards, and basically Saturn's rings will be no more. So again, astrophotographers, make the most of it now whilst you're able to take a picture of the beautiful Saturn, because before long the solar system will be bereft of beautiful ring systems. Not only will we have trouble trying to work out what's going on with Saturn, we assume that the rings will be lost, but when it comes to everything else, we tend to think of the solar system as being clockwork. That's sort of reinforced by the fact that, we've all seen orreries or a tellurium, and they give the impression that the solar system is just clockwork. If we want to know where Jupiter is in the future, we just have to know where it is now, and we can calculate that it takes this many years to go around the sun, so we can tell where it's going to be in thousands of years' time. Or if we want to know what the Star of Bethlehem was, we can dial the clock back 2,000 years and we can say, well, this planet was in the sky next to that planet, and we can do that quite reliably. Over thousands of years, that's not a problem. But over millions of years, we cannot predict where things are going to be. And when we look backwards, we can't tell where the planets were, for instance, 1 billion years ago. You may have heard some stories, some documentaries on the TV, where people talk about, well, actually, the order of the planets has changed in the past, and Jupiter has plowed through the asteroid belt, producing a lot of bombardment to a lot of planets. Similarly, we cannot tell where things are going to be. So beyond somewhere of order 100 million years, we cannot predict what the solar system is going to look like at all. We don't even know how many planets there are going to be. This is not about demoting Pluto. This is literally a planet might get thrown out of the solar system on a scale of order 100 million years. We just cannot tell. So don't be fooled by orreries which pretend that the entire solar system is clockwork. It's only clockwork on short time scales. On long time scales, everything is chaos. We cannot calculate if we have a system of more than one body, sun, planet, planet, moon, moon, etc. We cannot predict where they're going to be. On a similar time scale, 10 to the 8 years, things are going to change in our galaxy. At the moment, we are there. So there's the "you are here" sign. Roughly speaking, we're in between two rather dense spiral arms of the galaxy. The galaxy rotates on a time scale of order 100 million years. And so as we go round the Milky Way, we are going to drift from where we are now into one of these spiral arms. And these spiral arms are more dense than the region we're in at the moment. In other words, we're going to have a lot more stellar neighbors once we've moved into a spiral arm, which will take roughly 100 million years or so. What are the consequences of the Earth and the solar system being surrounded by lots of other stars? Well, remember what happened when Gliese happened to get close. It can produce distortions of the Oort cloud, and it can result in lots of asteroids and comets coming thrown our way. And the same could happen once we get into a situation where we have lots of stellar neighbors. If we look at the historical record, we find evidence that lots of species have become extinct on timescales of order hundreds of millions of years. There's some evidence that there's always some background extinctions, but there are clearly some fairly obvious spikes here, indicating that large numbers of species were killed at very particular points in past epochs. And the most famous one is perhaps the KT one, the Cretaceous tertiary boundary. That's the one that killed all the dinosaurs. So we survived that. I say we, not humans, but our ancestors survived that, and we've descended from them, but it was obviously bad news for the dinosaurs. And we think on a timescale of 100 million years, because we've got so many stellar neighbors at that point, we're going to get much more of these things. In other words, we're going to get almost certainly some extinction level events happening. So here's a nice artist's impression of a very large rock heading for what appears to be Italy on the left-hand side. So bad news for Italy, but of course anything that's really big heading for the Earth is going to be bad news for the entire planet, not just for a bit of the Mediterranean. Species, if this happens, and it almost certainly will at some point, species will be exterminated. And the only real question is, will that include us? Or, like the dinosaur killer, will we actually survive that particular encounter? More stellar neighbors means that we have more stars around us that could go supernova. Not stars that are hundreds or thousands of light years away, but close neighbors. And if a star goes supernova within, let's say, about 100 light years of us, it's been calculated that that could be a danger to Earth. 100 light years is too close for comfort. The radiation produced in a supernova could be bad news for Earth. If a star less than 20 light years goes supernova, that could conceivably end all life on Earth. Again, it could evaporate the oceans, remove the atmosphere, and it could easily sterilize every living organism on the planet. That's not particularly likely because 20 light years is fairly close. There are only a few stars closer than 20 light years. But if we have far more neighbors in the future than we have now, it is not inconceivable that that might happen. And for some reason, it seems to have stopped advancing. Just see why. Okay. Let me just get rid of that again. I think it's a Zoom problem. Is the click supposed to be a Zoom click or is it supposed to be a PowerPoint click? That's always the problem. So we've said that we'll have far more stellar neighbors in the future because we're moving into the spiral arm of our galaxy. So that means supernovae are going to be more common. We know there have been supernovae relatively close to us in the past because supernovae within 100 light years or so produce a particular isotope called iron 60. It's a particular isotope of iron which doesn't occur naturally on Earth, and it can be found in Earth sediments. And this particular isotope changes from iron to cobalt to nickel. In other words, it decays into a different element over a period of order a few million years. It doesn't occur naturally on Earth, so that means if we find some stuff on Earth, then A, it must have been deposited by a supernova because it doesn't occur naturally, and B, if we still find some of it around, even though it decays over millions of years, if we still see it, that means there must have been a supernova within the last few million or at most tens of millions of years. So because we do find this particular isotope called iron-60 in Earth sediments, that means we have definitely been close to a supernova in historical past. And we think it's likely to happen again on a timescale of order 100 million years or so. Throughout all of this, the moon is still robbing the Earth of angular momentum. The moon is still slowing the Earth down and using it to travel to orbit further away from the Earth. The length of the day is not 24 hours and a bit. It's now 25 hours. It is definitely slowed down, definitely time to decimalize the clock. We can't continue with this idea of 24 hours. 25 doesn't make a lot of sense, so maybe we need to change the timing. The distance from the Earth to the moon has increased as the Earth has been slowing down, and the distance from the Earth to the moon is now so great that it's impossible to get a solar eclipse. In other words, we need, if you ignore the distance from the Earth to the sun, which we don't think is going to change that much, if the moon is moving further away from the Earth, there will be a time when the disk is no longer large enough to cover the disk of the sun. So at the moment, there's a little bit of variation because the moon's orbit is elliptical and the Earth's orbit is elliptical. There's a little bit of variation, so we don't always get a total eclipse every time the moon comes close to covering the sun. Sometimes we get an annular eclipse. But if we go far enough into the future, the moon will never be large enough to completely cover the sun, and the best we can hope for is an annular eclipse where there's always a bit of sun peeking around outside the disk of the moon. So there will be a time when we no longer are able to see a total eclipse of the sun. So again, make the most of it for the time being. We know that the moon has a stabilizing influence on the axis of the Earth. We know from historical records that at the moment the tilt is 23.5 degrees, roughly speaking, and we know it hasn't really changed much, maybe a degree or so either way. In other words, this little animation shows you how much the tilt of the Earth has changed. You can see it just rocking ever so slightly backwards and forwards. You can see that a degree change really isn't much at all. But if the moon goes further away from the Earth, which it is doing slowly, day by day, year by year, if the moon is, let's say, 25% further away, the moon will find it really difficult to stabilize the axis of the Earth, and the Earth's tilt doesn't have to stay at 23.5 degrees. It could flop all over the place, in which case our seasons are going to be, again, all over the place. The variations in the Earth's climate could be extremely dramatic if the Earth is not fixed to a particular tilt. If it's pointing towards the sun at 90 degrees to the sun, it could be all over the place. So again, there are going to be very dramatic changes to the Earth's climate in the future. What about Voyager? We said earlier that Voyager is going to pass stars every 10,000 years or so. We're now looking a long time into the future. We're now looking something like 1 billion years into the future. The gold disk is probably going to survive that sort of timescale, roughly speaking. And the reason that survives, even though the Pioneer plaque doesn't, is because the gold disk that's on the Voyager, containing music and various speeches from various dignitaries, the gold disk is actually covered. And so that cover is taking the brunt of the impacts. The gold disk will probably survive. The bad news is the cover contains the instructions telling you how to read the gold disk. So the gold disk might still be readable, but any alien civilization that picks up the gold disk might have trouble deciphering what are we supposed to do with this thing with a lot of grooves in it. So again, the disk will have done its job. It will have passed thousands upon thousands of stars and planetary systems and probably Earth-like planets before it gets to the point where the disk itself can no longer be read. So maybe one of those thousands of planets and planetary systems could have somebody who's capable of reading these instructions within the time period of 1 billion years and telling where it is this disk came from. On this billion-year timescale, things are starting to change, not just on Earth, but in the solar system. The sun is starting to change. The sun is about 4.5 billion years old. 1 billion years or more into the future, it hasn't used up all its fuel yet, but it is starting to. It's starting to change. It is changing slowly from being a main sequence star, heading off towards being a red giant, in which it will swell up in size. As it does so, the luminosity is going to increase, maybe 10% for every billion years as time goes on. And if that sort of luminosity continues, that means the greenhouse effect is going to drive the Earth to a relatively balmy 80 Celsius or so. It's difficult to see how mankind can survive that. Do we go underground, or do we need to find another planet to live on? Or do we just call it a day and say, oh, well, we've had a billion years, that's fairly good. Certainly we'll need to think about something if we want to survive any further. We know the sun is going to swell up into a red giant, and the red giant is large even compared to the orbit of the Earth. So we can imagine the surface of the red giant not being 93 million miles away or 150 million kilometers. The surface of the red giant is going to be pretty close to the Earth. Maybe that's going to be a problem. So it's not going to be 80 Celsius on the surface of the Earth. Maybe it could be distinctly more than that. It is not absolutely obvious whether the expanding sun is going to engulf the Earth or not. It's often said that the sun is going to expand and be large enough to engulf the orbit of the Earth. That is probably true, but you have to bear in mind that as the sun expands and goes towards its red giant phase, there's going to be very strong solar winds. They are actually going to carry mass away from the sun, so the mass of the sun will actually start to drop at this point. If the mass of the sun starts to drop, there's less gravity pulling on the Earth, which means the orbit of the Earth is going to get larger. So in this cartoon on the left, we can sort of see what's going to happen, not to scale. There's the sun in the middle and the Earth in its orbit. As the sun starts to grow larger, it does start to get large compared to the orbit of the Earth, but the Earth is moving away from the sun because of the reduction in the mass of the sun. So at some point, the sun indeed will be large enough to engulf the orbit of the Earth, but the Earth won't be there anymore. The Earth will be further away from the sun. So we don't actually know, but maybe the Earth will survive even after the sun goes through its red giant phase, a few billion years into the future. Once the sun has become a red giant, it will eventually slough off the outer layers. They'll be lost to the interstellar medium, and what's left is the core of the sun, a very hot white object, a white dwarf. No nuclear fusion anymore. It's just a hot object which is going to slowly cool down. Mainly made of carbon, probably. That's the last element to be made in the center of the sun before it finishes its thermonuclear fusion on a scale of many billions of years. We're not too sure what's going on in the center of a white dwarf, but if it is carbon and if it is under very high pressure, perhaps it's a diamond. That's an active area of research at the moment, trying to work out what white dwarfs are actually made of. If we survive, it's not impossible. The sun will expand to a red giant, then the red giant outer atmosphere will be lost, and the sun will cool off again. If the Earth survives, it has another problem, and that is the core of the Earth will continue cooling. It's not the sun keeping the core of the Earth molten. At the moment, we have a molten core, which gives us a dynamo, lots of iron spinning, lots of molten iron spinning, gives us a dynamo, which generates the Earth's magnetic field. It's not the sun that's keeping the core of the Earth molten and has been doing for billions of years. No, it's radioactive decay in the core of the Earth. Eventually, that radioactive decay will no longer keep the core of the Earth molten. Eventually, it will solidify, much like it's thought that the core of Mars has solidified, and hence Mars has no appreciable magnetic field. Eventually, we will have no appreciable magnetic field, which means we'll then be subject to radiation from either the sun, which may not be a problem anymore if the sun is a white dwarf, but it will be a problem because we'll be subject to cosmic radiation. And without a magnetic field, we'll have essentially no protection. So we've survived the sun going a red giant. Maybe we can survive the loss of a magnetic field somehow. Maybe we can generate one artificially. But then, as if to add insult to injury, we then find that the Andromeda galaxy is going to go crashing into us. On a similar timescale of billions of years, the Andromeda galaxy is thought to be heading our way, not necessarily a head-on collision, but we're not absolutely sure. But the Andromeda galaxy is going to start looming large in our sky on timescales of order 3 to 4 billion years or so. When they start to pass through each other, it's unlikely that stars will impact each other, so our sun is not necessarily going to be hit by another star, but there is going to be an awful lot of disruption as one galaxy passes through another. There's going to be a huge amount of new star formation. Far from being the cataclysmic end of days, this might be a sort of rebirth, if you like, of the galaxy. So they're going to pass through each other, and then gravity is going to take hold and pull them back together again, and eventually settle down into a rather amorphous, probably not a spiral galaxy, with a couple of nuclei. The supermassive black holes at the center of our galaxy and the Andromeda galaxy eventually are going to merge into one. So that's not necessarily catastrophic for our sun. Even if the sun gets ripped out of the galaxy and moved on, all the planets will go with it. So it's not necessarily a problem to have galaxies collide with each other. All of this time, assuming that the moon doesn't get pulled away, the moon is eventually going to lock the Earth into a system whereby one day is the same as 1 month. In other words, the length of time it takes the Earth to spin once will end up being the same as the length of time it takes the moon to go round the Earth. And by the way, this is a real picture. It looks like it's just been photoshopped, but no, this is a real picture taken from a long way away, in which the Earth the moon just happens to be a little bit in front of the Earth to give you a nice sense of scale. So in other words, there will come a day when the Earth is tidally locked to the moon. The same face of the Earth will always face the moon. There will be some points on the Earth in which the moon will always be in the sky. The moon will not move in the sky. From certain points on the Earth, the moon will be up there. From other points on the Earth, you will never see the moon. It will never rise above your horizon, because the Earth is spinning at the same rate that the moon is going round the Earth. So the idea of the same side of the Earth always facing the moon mirrors what's been happening to the moon. Remember, when we look at the moon, we always see the same face. The same face of the moon always points to the Earth. Eventually, it'll be the same the other way round. What's going to happen on a slightly larger scale? Well, we're now here at roughly 1 trillion years, 10 to the 12 years. What's going to happen in our region? There's our galaxy at the center and some of the galaxies that are not too far away from us, called the local group of galaxies. If we look at what's going on with the Milky Way is quite a big galaxy, and it has lots of smaller satellite galaxies around it. Those are going to get eaten in much the same way that we are going to collide with Andromeda and merge together. Eventually, Andromeda and M33, the Triangulum galaxy, are going to merge into one humongous galaxy. Everything in the local group is going to end up in one place. Basically, galaxies are cannibals. They will eat each other, and the largest one wins and ends up mopping up all of the smaller galaxies. That's how galaxies evolve. That's how galaxies grow. We learn that by looking at galaxies in the last few billion years and many billions of years ago, by looking back in time with the Hubble Space Telescope or something like that. So we learn that's what's going to happen. And we are fairly sure that on this time scale, there will only be one galaxy in the local group. In terms of other galaxies in the universe, well, at the moment, it's possible to image galaxies, even if those galaxies are receding from us faster than the speed of light. That was one of my lockdown challenges, to try and image with a camera, but not a telescope, a galaxy that's receding from us at twice the speed of light. So we know that that is not a limit. It is possible to image objects that are close to us. It's possible to image objects a long way from us, even if they're receding faster than light. But when we think of the Hubble Space Telescope image, in which we've got a couple of stars that are part of our Milky Way, and pretty much everything else in the image are distant galaxies, there will come a time on this time scale, trillion years into the future, where the universe has expanded so much that none of these distant galaxies will be visible to us. They will be beyond our horizon. In other words, a picture from the Hubble Space Telescope, instead of looking like this, is eventually going to look a little bit different. The stars in our galaxy will still be visible, but all of the galaxies that are more remote than that, in other words, every other galaxy in the universe, will eventually go beyond our horizon. We won't be able to see them. Bear in mind that if any civilization comes into existence on this timescale, it's the same for any other galaxy. So if a civilization comes into existence a trillion years from now, if they build themselves a Hubble Space Telescope and they ask, I wonder what's out there, let's go and photograph it, they will see nothing other than the stars in their own galaxy. So they will not even be aware of the fact that there are other galaxies beyond their own galaxy. We are lucky enough to be at a time where we can actually see all these galaxies out there, and we can see that the Milky Way is just one of a trillion galaxies. But eventually, the expansion of the universe will make that impossible. I said that it takes 3 minutes to make all the hydrogen in the universe. After a trillion years or so, it's nearly all gone. So there'll be no new star formation. It is thought, maybe, perhaps, if you haven't got hydrogen to make stars, maybe you'll start making stars out of something heavier. And some people have hypothesized that if you start making stars out of heavier elements, it might be possible to generate a star with nuclear fusion at the core, but the surface temperature wouldn't be tens of thousands or thousands of Kelvin. It might be possible to make a star where the surface temperature is hundreds of Kelvin. And if it's below 273 Kelvin, that means ice could form. It might be possible to make a star in which there's thermonuclear fusion at the core, but ice in the atmosphere, a frozen star. And if you're a fan of Disney, if I say frozen star, you might think of the picture on the left. That's the wrong picture to have, so if that's what's in your head, just let it go. Okay. Sorry. So what we're talking about is a star which might still undergo thermonuclear fusion, but would have ice, or at least the temperature of ice in the atmosphere. That's just a hypothesis. But before going any further, and yes, we do have a little bit further to go, bear with me for a little longer, we have to remind ourselves what the universe is going to do. This is the relative size of the universe as a function of time, and the different colored lines tell us what the universe might be doing depending on how much stuff there is in the universe. And also, the amount of stuff in the universe tells us what's happened in the past. If we have a look at and remind ourselves that that circle is now and a relative size of 1, the age of the universe depends on what's in the universe. In other words, our estimate of how old the universe is depends on what's out there. If there's a lot of matter out there, then we can expect the expansion of the universe to increase for a while, but then start to decrease into a big crunch. We don't think that's the situation. There is not enough mass. We don't have to worry about 5 watt. Let's just take it as 5 units of mass. Let's not worry about what the units are. If there's a lot of matter out there, then the universe might come into a big crunch. In other words, it'll expand for a while, but then gravity will win. But if there was less matter, then we'd end up on the green line, and it would keep on expanding forever. We think we're actually on the red line. We don't know for sure, but we think we're on the red line, which means the universe will continue expanding as time goes by and get larger and larger, and not only keeps expanding, but expanding at an ever-increasing rate, a so-called flat universe. So let's assume that we're not in the big crunch scenario. Let's assume the universe doesn't end. Let's assume that it just keeps on expanding forever. And we're now going to change these numbers at the top. Don't worry, we're going a bit quicker now. Instead of each box being 10 times further into the future, each box is now 1,000,000 times further into the future. So we're talking about a zillion years and a gazillion years. I don't know what the names are. So they're just big numbers, and we're just going to rely on the digits to tell us how far into the future we're going. Before we took this detour into what the expansion of the universe looks like, we said after trillions of years, the hydrogen is running out. If the hydrogen is running out, there are no new stars. Stars might live for a long time, but they don't live forever. So what does that mean? There will come a time, there will come a day, when the stars will stop shining. The age of starlight will come to an end. The stars will still be there, dead stars. They won't be shining anymore. There won't be any stars to see in the sky, but the stars are still there. They are dead stars, white dwarfs, neutron stars, black holes. They will still be pulled with gravity and still be going around their galaxies, even though they are no longer shining. Some stars will actually be removed from the galaxy. We've seen that before. We've actually seen, by mapping out the velocity of stars, we see that some stars are actually being thrown out of the galaxy. We think that's going to be a lot more common in the future. There are no nuclear reactions going on at the centers of neutron stars or white dwarfs. So basically, white dwarfs will cool down. They're white only because they start off hot. Nothing is generating any energy in the core. They will cool off and eventually become black dwarfs. And it's hard to see what's going on here. Let me make it just a little bit brighter. It's basically just a lump of carbon. That's all it is, and it will just get colder and colder and colder. Some stars will be eaten by the supermassive black hole, SMBH there. Some stars will be thrown out of the galaxy. Any that aren't thrown out of the galaxy will probably be gobbled up by the supermassive black hole at the core of a galaxy. What's going on in the middle of these galaxies? Well, magnetic fields have been mapped out in one galaxy by SOFIA, an infrared telescope in the back of a jumbo jet. SOFIA is Stratospheric Observatory for Infrared Astronomy. So an infrared telescope in the back of a jumbo jet has actually mapped out the magnetic field lines close to the supermassive black hole in the center of this particular galaxy. And it's thought that these magnetic field lines are funneling the matter into that central black hole. So stars are ejected, what's left funneled into the supermassive black hole. So we end up with essentially just a black hole in the galaxy. What's happening to all the atoms out there? Well, it is thought that, well, we know what an atom is. It's protons and neutrons surrounded by electrons. It is thought that perhaps protons decay. We don't absolutely know that. If they do decay, they decay on very long time scales. We're now talking about 10 to the power 36 years, ridiculous time into the future. If protons do decay on this time scale, all atoms will fall apart, and there'll be no atoms anywhere in the universe. We'll just end up with a collection of fundamental particles. The time scale over which that happens, we're not too sure about. It's probably not less than this number, but we don't actually know. Even if atoms do survive, even if protons don't decay, then stars will still evaporate. So black dwarfs, for instance, will eventually evaporate, leaving no atoms in the universe. Neutron stars already are not made of atoms. Black holes already are not made of atoms. White dwarfs or black dwarfs are the last objects that are made of atoms. And if they evaporate, there are no atoms left anywhere. It's hypothesized that, well, maybe what's going to happen is all the elements in all the dead stars are going to eventually end up as iron. That doesn't seem very likely because, generally speaking, we tend to think of thermonuclear fusion requiring high temperature and high pressure, like at the core of our sun. If all these stars are basically dead and cold, how can they fuse? Well, fusion is still possible. It's just very unlikely and hence very slow. But look at the time scale. We're talking about 10 to the power 42 years, millions of millions of millions of millions of years into the future. Even if it's very unlikely to happen, if you wait long enough, maybe everything will end up as iron before all atoms disappear from the universe. Supermassive black holes are going to merge, just like the supermassive black hole at the heart of our galaxy is going to merge with the supermassive black hole at the heart of the Andromeda galaxy. When the galaxies collide, the black holes will merge. That will be going on everywhere. In other words, we'll end up with supermassive black holes pretty much everywhere in the universe. But black holes are not eternal. You might think the end of the story is the entire universe just turns into black holes. But that's not quite the end of the story because black holes do not last forever. Even black holes will evaporate, providing that you wait long enough. And look at the ridiculous time we're now talking about, 10 to the power 66. Why do they evaporate? Well, I've just got a few more minutes to tell you that story. Our understanding of how the microscopic world works when we look at the so-called theory of quantum mechanics or quantum theory That tells us that you can borrow energy from nothing and make stuff. Maybe that's how the universe came to be in the first place. You borrow from nothing and you make stuff. So it's possible to borrow energy, make matter and antimatter, and then they annihilate and make energy again. You pay back the loan. You borrow from nothing, make stuff, and then you pay back the loan a little while afterwards. How does that help us understand black hole evaporation? Well, Hawking said, what happens if we have a black hole event horizon? Anything that falls into that circle is lost into the black hole. What happens if we borrow from nothing and make two particles, but what's happened? One of them has gone into the black hole and the other one hasn't. So it looks for all the world like something has come out of that black hole, because now we have something that cannot annihilate with its other half, as it were. So there appears to be a net flux of something coming out of the event horizon of a black hole. And this has now been called Hawking radiation after Stephen Hawking, who first proposed it. Strictly speaking, not proven, but it seems very likely that that will happen. So that means all black holes evaporate, and the smaller ones evaporate faster than the larger ones. So as black holes evaporate, radiation levels increase. It becomes smaller, radiation goes up. It gets smaller still, radiation levels go up. It gets smaller still, radiation levels go up. So black holes end their lives in a flash of radiation. And even the big ones, even the supermassive black holes, which might be trillions of solar masses, they are huge and don't radiate very fast. Even they will evaporate eventually if you go far enough into the dim, distant future. It will take trillions of times longer than small black holes to evaporate, but as best we can tell, it will happen. And finally, we reach, after a little over an hour, the end, question mark. In other words, where do we say the universe ends? Well, strictly speaking, the universe is eternal. In the sense, there is no point at which we say this is the end. But if we ask ourselves what's happening on a time scale of 10 to the power 100 years, 10 to the power 100 is a Google. Not that one. They spelt it wrong when they set up the company. They intended to spell it that way, but somebody got the typo wrong. So a Google with an OL is 10 to the power 100. And after a Google years, all the black holes have evaporated. So effectively, everything gets converted ultimately into black holes. Regardless of how you mix everything together, white dwarfs will evaporate, neutron stars will evaporate, everything ends up as black holes. All the black holes merge together to give you supermassive black holes, but even they eventually evaporate. And after a Google years, that's it. There are no more objects in the universe. Even the biggest black hole has now evaporated. So at this point onwards, nothing happens from this point until the end of time. And so you could argue time itself becomes utterly meaningless, because if there's nothing out there and nothing happens, how can you possibly measure the passage of time? And just to remind you that a Google is a very big number, I don't often do this, but let's just write it out in zeros. That's how big a Google is. Remember, that's 1,000, that's 1,000,000, that's 1,000,000,000, that's 1,000,000,000,000, that's 1,000,000,000,000, that's etc. You can see that a Google is so much larger than, for instance, how old the universe is now, 13.8 billion years. That's only that much, only that many zeros, 10 zeros. A Google is a long way into the future. And it's difficult to see that there's any real meaning on talking about timescales greater than a Google years. So what can we say about eternity? Well, not much, but Woody Allen has a good stab at it. Eternity is a very long time, especially towards the end. But I've seen another quote which tries to put mankind in perspective. We exist now, 13.8 billion years after the Big Bang, and a long time before the universe comes to an end. And this quote I quite like. A human is a system for converting dust billions of years ago into dust billions of years from now, via a roundabout process, which involves checking email quite a lot. I thought that is a good way of putting the whole thing in perspective. So let me finish with an epilogue. you could say we live in a golden age. The sun is middle-aged, stable, it's well-behaved. The moon is at just the right distance to stabilize the Earth's axis and hence the seasons and the climate, and it's just the right distance to give us the spectacle of a total eclipse of the sun. Thanks to evolution, we're able to explore and discover and hopefully understand the universe around us. And we can do that by visiting our closest neighbors and by building telescopes that allow us to see galaxies that are billions of light years distant. We have to remind ourselves that we could not have arisen, humankind could not have arisen in the very early universe, as we needed lots of generations of stars to start with hydrogen and make helium, and then use the helium to make carbon and nitrogen and oxygen and silicon and phosphorus and all the other elements which are needed to make a complex, intelligent life much as us. And we've just seen that the future, trillions of years from now, will be dark and really, really boring. So if that's the case, the best time to exist is now. Thank you all very much.